Hello everyone, this is Kimia-Tasnia. Welcome to the presentation of EEE 6406 Advanced EDA. I am going to present a paper from SLT2 topic. The paper is titled of 12 nanometer agile design SoC for swarm-based perception with heterogeneous IP blocks, a reconfigurable memory hierarchy, and an 800 MHz multiplane NOC. The paper is presented by a group of authors from Harvard University, Cambridge, the Columbia University of New York, and the IBM research from New York. This paper presented an agile design domain-specific SoC in 12 nanometer CMOS technology for the emerging application domain of swarm-based perception. What is swarm-based perception? So this is a vehicular swarm perception system for autonomous driving. So in this system, a group of vehicles is involved in the system for a collective perception capabilities. So this system is collecting data from a number of vehicles and for the perception communication, which reduces the false prediction to a number of times. And this swarm-based perception includes a CNN for the object detection, the A50 and Viterbi decoding system for signal processing and wireless communication, and for the general purpose computing for the decision making. This work features a heterogeneous style-based architecture where this simplifies the reuse of the OSH open source hardware IPs. So this is their main motivation. So I will elaborate in the following slides. And they actually mitigate the complexity of the heterogeneous SoC design in their proposed design by decoupling the design and integration of the heterogeneous IPs. This is the overall figure of their heterogeneous system. So in this system, for this swarm-based perception application domain, they used a number of IPs from the open source hardware. So there is the RISC-V processor, the accelerator from a number of third parties. So each IPs are integrated in a tile socket. So this is their innovative idea for this SoC, that they integrated this system in a tile-based system. So each IP is integrated in a different tile, and these tiles are connected to each other with a NOC router, the network on chip router. And this helps a lot for the seamless integration of the IP, because these tiles can be function individually and they can be function and connected for different configuration. I will expand more in the following slides. So this is the overall architecture of this domain-specific heterogeneous system, the elaborated architecture. So you can see that this is a 4x4 tile connected by a 2D mesh multiplane network on chip. So there is 4 RISC-V processor, 3 NVDLA accelerator, 3 FFT accelerator, and 1 Viterbi accelerator. And there is 4 LLC for different cache coherence memory configurability. And they are connected through the modular FPGA to the DDRM DDR3 memory. And there is one tile for the host IP, which has the Ethernet UART and the ROM. So each IP is encapsulated in a separate tile socket. So this is the tile socket, and this is the NOC router, which connects them to a local bus system, and like they are connected to each other. And any subset of the memory tail can be selected at the runtime. It is not necessary that we need to utilize the whole SoC together or all the blocks together. We can use the subset of the memory blocks for the different configuration or different functionality. So this is the design optimization system of this agile SoC design. So the different software is connected to the tile socket, and they are very easily integrated to the SoC. And since they are already taken from the OSH system, so they are using the synthesizable design to avoid any manual layoff. and layout effort. And the cogeneration of corresponding test bench is also provided from the FPGA emulation. So the test bench is also provided through this emulation, and they are evaluated for the functionality of these IPs. And after that, the next one is the physical design of the each IP. So that physical design is accomplished with the hierarchical ILM-based timing closure flow. So in this flow, each IP is signed off individually, though not at the same time. So they can be placement and routed individually, and they can be signed off separately. So this flow actually reduces the time of the configuration a lot, and this whole design only took 4 months with less than 10 times full-time designer. So yep, the previous SoC-based design with the similar tile-based system took 7 months, but this design outperforms in 4 months. Another feature which is showing that how they exchange data among the different heterogeneous tiles. So there is a multi-plane system. There is 6 planes. So plane 1 to 3 provide the coherence channel between the CPU accelerator and the LLC partitions, and the plane 4, 5 support the DMA access, the direct memory access for the accelerator, and plane 6 is dedicated for the interrupt and the memory mapped input, output, and the registers. And there is the memory configurability for 3 different configuration for the cache coherence modes, which is the non-coherent DMA, LLC coherent DMA, and the coherent DMA. So you can choose the different configurability for the accelerator to access the memory hierarchy through this different coherence model. Finally, the communication synchronous GLS blocking strategy, which is another important feature to this SoC. So what is this strategy is telling that is each IP tile is synchronous to a local clock and a local power system. Again, the NOC is in a global power domain, which is synchronously driven by a chip-wide global clock. To support the heterogeneity of the each IP block, the frequency of the tile and the frequency of the NOC need not to be the same. So they can be adjusted dynamically and independently. So that's how they are making it globally asynchronous. So you can choose or you can decrease or increase the frequency for individual tile at any time. And if you want to take a closer look to the NOC router, so inside the NOC router, there is a crossbar routing, which is routed to the 4 neighboring tiles and to the local tile via the asynchronous interface. So that's how the interface is connected to each other. So this GLS is giving the flexibility of the frequency for each tile, and it reduces the energy a lot, which I will show in the following slide in the result section. So the first figure of the result is showing the performance and energy evaluation for each tile. Like they evaluated when they are deploying accelerated to the CPU and when the CPU is operating standalone. So with the integration of the accelerator, for the A50, the latency is reducing 71 times and the energy is reducing 233 times. For the Viterbi, it is 20 times in latency and 56 times in Viterbi, in energy, I'm sorry. So the next figure is showing the GLS method outperformance or the benefit from that strategy. So here, this system is showing that we can choose the different configurability of the tiles, like for different number of FFT and different number of memory, that how they will be connected. And with this configuration, the latency varies. And also, as we can change the frequency anytime, like for when the workload is memory bound, the frequency of the A50 can be reduced from 1.2 gigahertz to 470 megahertz, which maintains the same latency but reduce the energy 2 times. So yep, you can do it with adjusting the frequency of the different tile. The next one is the overall performance of the SoC with this agile tile-based system. So if they have a significant performance improvement of 7 times in latency and 62 times in energy, other than using the high-end FPGA. So this is really good performance, I would say. And finally, this is our overall chart of comparison of this work with some other SoCs of the homogeneous system. So after integrating the different IPs, it still uses the process of 12 nanometer technology and the area of 21.6 millimeters square. And the data flow bandwidth, the data flow rate is 281 gigabyte per second. And the NOC power is 7.2%, which results an overall power of 240 milliwatt to 1.83 watt, which is much reduced than the other system. So it really saves a lot of power and energy for this system, and also a much better improvement in the latency. So thank you all for joining with me. Have a great day. Thank you.